Right, so I'm working on bioacoustic monitoring of invasive species, and I'm based out of the software engineering department. So I'm going to be talking specifically about computational bioacoustics, how how we can develop improved tools for the monitoring of species that are typically more challenging to monitor. So the target species are of course possums, mustelids, and rats. The majority of my work is focused on possum vocalizations because they are far more vocal than the other two species. But there's still a major challenge. So when I started my research a few years ago, there were no existing data sets on these species. So what we did was we went through the process of actually gathering that data ourselves. So we started off in Governor's Bay using the setup on the right. So this is Cacophony Project's thermal camera, and we have a microphone array that's set up on top of it. So it has a similar setup to what Brittany's been using. The alerts are being played through a speaker, and the thermal camera is actually pointing at that speaker. So the reason we initially went with a microphone array was that so it has 6 microphones on it, and it can also determine the direction of the sound. So we thought we'd have multiple vocalizations, and we'd be able to figure out which direction those vocalizations are coming from. So we could figure out if we have, a single animal vocalizing multiple times, or multiple animals at the same time. And this didn't really go to plan. We found that the vocalizations were far sparser than we initially thought. We had this set up for about a month and only really recorded a few awesome vocalizations that we were certain about. So then we kind of shifted tactics, and we moved to using audio muff microphones, though that's shown there on the left. This is just a really simple device. It's an omnidirectional microphone, and it has software built so that you can set it to trigger for certain intervals at certain times of the day. So we set this microphone, or 3 of these microphones, up out at Lincoln, and we've been collecting data for quite some time now, and that comes with its own challenges, which I'll get to soon. But first off, why do we care about acoustic monitoring of these species? So the first one is real-time detection and response. So this ties in nicely with what Brittany's working on. So the idea being that you can have multiple of these devices set up in the field that are detecting these species in real time, and then can adjust luring strategies of surrounding devices in response to that. So you can develop highly customized and specific lures. There's also the monitoring of ecological health. So, of course, you're looking at reinvasions and also proof of absence testing for these target species, but also biomonitoring of bird species, and giving some kind of index of the biodiversity of the ecosystem. There's also more accurate occupancy and abundancy modeling. So using these techniques to determine if the animal is present, and if so, in what abundancy, as well as behavioral information. So as I mentioned, when I started my research, there just wasn't data available in these species. So more data that becomes available, the more we can learn about different vocalization types, and what it means for the animal's behavior. So currently we have these microphones set up at Lincoln, and we're collecting over 100 hours of audio each week. And that's already a challenge for a human to go through and analyze all that data. So you can imagine if you want to extend this to a large scale monitoring operation where you have hundreds of thousands of these devices spread out across the landscape, you can see how that scales, and that becomes a really challenging problem. So we're going to talk about a human-in-the-loop annotation tool that we've been working on. So one of the key reasons that we've gone with the human in the loop tool is because we want to combine the efficiency of deep learning models and computational tools, but also the annotation accuracy of human analysis. And these have some key benefits compared to a deep learning approach, which is currently a bit limited. So if a human is analyzing audio data, they only need one reference, and they can use that reference to find similar features within data, given enough time. And also, they can scan through audio and pull out features that they might not have heard before. Whereas a deep learning model really struggles with this. It will often miss those features that it hasn't seen before, or assign it to an incorrect class. So by combining the two, we're hoping to get the best of both worlds. So this is the tool. You're able to load full field recordings, and it'll automatically scan through all the data, and it'll extract these features of interest. And the features of interest here are shown in the orange and blue blocks. So these are 5-second segments. These segments are then fed through a deep learning model, which applies a label to that data. And then the labeled data is then presented to a user who can go through all that data, verify that it's correct, and make adjustments if it's not. That data is then fed back through the model, and it improves the model over time, which then improves predictions and annotation efficiency. So just to give you a brief overview of the results, using a very limited data set, we've been able to achieve over 98% accuracy for possum classification versus not possums. Using the segmentation method, we've been able to reduce the empty space in field recordings by up to 90%, which is a huge reduction in the amount of human time that has to go into analyzing that data. It's also far more efficient than alternative approaches. So I'm just going to briefly talk about what this tool is doing under the hood, how it operates. So I'm going to be talking, just to begin, we'll talk about audio representation. So we're using a spectrogram, which is a 2D representation of audio. It's a time frequency representation. Just as an example, if you look at the image on the right, you see the waveform, the one-dimensional waveform on the top, and the spectrogram shown below. So it's far easier when you look at these two options to identify the vocalization within the spectrogram. And the blue is showing possum vocalizations here. So that's the audio representation that we've chosen to go with the annotation tool. It's worth noting that there's this is just a little bit of how the spectrogram works, but it's worth noting that there's also other types of audio representation. So it's become more popular in recent years to actually just use the waveform itself, which can be a little bit counterintuitive given the previous example, and how difficult it is for a human to look at the waveform and pull out features. Whereas a model, it doesn't have that same limitation. It can scan through that data. It can build up a representation on its own. So just to compare these two options, so spectrogram versus waveform, spectrogram is far more interpretable. You can also apply models being trained on image processing, and you can treat the audio as if it were an image and feed it in the same way. Whereas with a waveform, you need more data because you're training the model to actually extract those features, and it's also less interpretable to a human. So segmentation, we're using a method called wavelet packet decomposition. This is the same method used by Avia and Z, if you're familiar, applying it to birdsong segmentation. So this method, it decomposes the signal into a set of approximate and detailed coefficients. And you can basically think of those coefficients as like a low and a high pass filter, and it can continue to decompose the packets to the desired resolution that you want. So what we're doing is we're decomposing the full 5-minute field recording, and we're also decomposing a 1-second reference feature. So say a 1-second possum vocal And all we're doing is we're taking the feature or a set of features in this case, and we're convolving, scanning those features across the full field recordings and pulling out regions of high correlation. So once we've pulled out those features, we've set them to 5-second segments. They're then fed through this model. So interestingly, we're using the spectrogram as an input to this model, and we've tested between spectrograms and the waveform. And in this case, with the amount of data that we have, using the spectrogram still gives the best results. So this is a transformer-based attention model. So these are becoming quite popular in recent years. So attention mechanisms, they basically learn which regions of the input to pay attention to. So using this method, we've been able to achieve over 98% accuracy on awesome classification. And then just the final thing I'll touch on is outlier detection. So we're using frequency septual coefficients, and this can just be thought of as another audio representation type. And so what you end up with is a set of coefficients over time, and that gives you this colorful plot up the top, and that can just be thought of as a fingerprint that shows the quality of that audio signal. And what we can do is we can apply methods like principal components analysis and actually take all that high dimensional data and squish it into a two-dimensional point. So each of the green, red, and blue points are each 5-second segments. And what we can do is apply a silhouette score to each of those points to figure out if they fit well within their cluster. And that's just a simple way of visualizing the data and seeing if there's any outliers, any mistakes that the model has made, and going through and correcting them. Right, thank you.